Equation solving and modeling. Modeling, modeling means word problems, everybody's favorite, right? Word problems. I'm not sure if I'm going to be using my calculator today or not, so we'll just play it by ear and see what happens. Alrighty. I like solving exponential equations algebraically. That means I don't have to touch a calculator, right? That makes life pretty easy. Solving algebraically, trying to figure out what x is. Well, shouldn't be that bad. Whenever you're trying to get x by itself, you're going to be using PEMDAS in reverse order. So the first thing we're going to have to do is divide both sides by 20. Divide both sides by 20 is going to give us 1/2 raised to the x over 3. What a weird thing, fraction raised to a fraction, equals, and 5 over 20, we might as well reduce it to 1/4. So back in the day, we talked about solving exponential equations, and we said the only way we can do this is if the bases match. We needed the same base on both sides. Well, I can't, quote unquote, reduce 1/2. However, 1/4 can be written as a 1/2 to some power. Because 4 is 2 squared, 1/4 is 1/2 squared. And now we have the same base on both sides. When we were solving exponential equations the very first time, what I said was, oh, well, once the bases match, you could just forget about them and just write the exponents equal to each other, right? But why?
They cancel out.
I'm sorry?
They cancel out. You don't
Yeah,
really forget it.
but they're equal to each other, but we can't just cancel them out. We can't just say they cancel out. What's the algebraic process that allows us to not worry about them? How do I cancel them out? Yeah, you use a logarithm. Since they have the same exponential base on both sides, we're just going to use a logarithm of the matching base to cancel these out. Like McKinley said, we got to cancel them out. So we're going to use log base 1/2. That's a weird thing to say. And I'm just going to kind of squeeze it on here like this, log base 1/2. And I don't know, log base 1/2. There we go. Log base 1/2 of both sides will cancel all that junk, and you just get x over 3 equals 2. So clearly, multiply both sides by 3 is going to give you x equals 6. Yay, easy math. Not too bad, right? We really did this before. I just wanted to use logarithms to cancel the exponential bases this time. Now this next one's got a bunch of e's in it. So if I want a decimal answer, clearly going to have to grab a calculator. But I wager, yeah, we can solve this exponentially, algebraically, for the most part. At the end, I will grab a calculator, but hold on to your socks, okay? So first we write it like that because sideways fractions, yeah. This makes it really obvious. I think the first thing that you should do is get rid of the fraction, right? Multiply by 2 on both sides. So we get e to the x minus e to the negative x equals 10. Woo! Okay. Realistically, you would use a calculator to solve this, right? Especially now that you have the ability to use a graphing calculator, you would have just set you would have set that ugly fraction equal to 5, 2 different lines, and asked the calculator where they intersect, right? But we're trying to flex our brain muscles here, so let's get as far as we can algebraically before we have to touch a calculator. I'm looking at this, and it is just screaming to me that it is a quadratic. Yeah. You see, it jumps out at me as quadratic, but why? Be honest with you, because we do this a lot in IB. So I've just kind of gotten used to seeing this. You don't recognize it as a quadratic yet, though, do we? What if I did this? What would you want to do from here? I just used the negative exponent, brought the e to the x to the bottom, so it'd have a positive exponent. You guys don't like fractions, right? So what would you do? You multiply everything by e to the x, you'll no longer have a fraction. So let's just go ahead and set it up like that. Multiply everything by e to the x. So I'm going to take this e to the x and I'm going to distribute it to all three places. At the front, you guys are cool with the fact that e to the x times the e to the x is e to the x squared, right? I could write this as e to the 2x, but you know what? I just don't want to. I'm going to write it as e to the x squared for now. And then minus 1 equals 10 e to the x. Does it look more quadratic yet? So what I'm going to do is I'm going to bring everything to one side. E to the x quantity squared minus 10 e to the x minus 1 equals 0. And you're going, Mr. M, how in the world could I possibly solve something like this by hand? Well, why don't we make a substitution? Why don't we call e to the x, why don't we just say e to the x is m? So we'll come way up here. Let's say let m for McCutcheon equal e to the x. If you do that, what you're going to get is m squared minus 10m minus 1 equals 0. Looks like a quadratic now, doesn't it? And is that going to factor? No. So how can we solve it? Oh yeah, the quadratic formula. But instead of x equals, it's going to be m equals negative b plus or minus root b squared minus 4ac all over 2a. Of course, a is 1. So what does that give us? Square root of 104 in there? Yeah. So 10 plus or minus the square root of 104, which, by the way, is just a little bit more than 10, divided by 2. And this would have been probably, I mean, I would have grabbed a graphing calculator a long time ago, but this would have been the first places that I was looking for a decimal answer. But you know what? Again, we're just going to keep flexing that brain muscle, show how smart we are. And let's reduce that radical. There is a perfect square that goes into 104. It's not very large either. Guesses? It's 4, yeah. 4 goes on 104 26 times. So 10 plus or minus the square root of 4 times 26 divided by 2. Of course, you get to take the square root of 4 out. Comes out as a 2. So we have m equals 10 plus or minus 2 root 26 over 2. And yay, I can divide both those things by 2. So it's actually 5 plus or minus root 26. So it is 2 answers. But oh, wait a minute. That's m, right? We're solving for x. M is e to the x, correct? So what we have here is that e to the x equals 5 plus or minus root 26. Square root of 26, what do you know about that number? Just in general, what do you know about it?
Pretty close to 25.
It's pretty close to the square root of 25. Is it going to be bigger or smaller than the square root of 25?
Bigger.
A little bit bigger. So what we know is that the square root of 26 is just a hair bigger than 5, right? So 5 minus a number that's a hair bigger than 5 is negative, isn't it? Right? E to the x can never be negative values. E to the x's range is greater than 0, which means the 5 minus root 26 is an impossibility. All we're left with then is, and I don't know if you want to write like impossible or something like that. I don't know how you want to do that. Well, I'm sorry? Because if you graph e to the x as a horizontal asymptote at the x-axis, e to the x is always going to give you positive results. So it's impossible for e to the x to be a negative number. What we're left with here is e to the x equals 5 plus the square root of 26. And how do I get x by itself? What kind of log? What kind of log? What's going to cancel e? ln. Log base e, a natural log. So we use the ln of both sides, and what we get is that x equals the ln of 5 plus the square root of 26. Look at you geniuses. By the way, that's about 2.312.
I hate everything.
We do things like that in IB all the time. It's very common, actually. Boy, oh boy, that was fun.
It's an error.
Yeah. Fun for us nerds. What do you think?
That was painful.
It was not painful. You shush. It was awesome. Okay. I don't know. Maybe, maybe not. He wants to know if it's going to be on the test. We shall see, won't we? Well, you'll know if it's on the test or not if it's on the practice that we can do tomorrow. Well, we can't just see answers. That's cheating. That's cheating. You can't just see answers. You have to solve for them algebraically.
But it doesn't ask to solve algebraically.
Yeah, but it's not just 10. You see, that's half the answer.
Ooh,
It's actually plus or minus 10. All right, so, but we don't want to just see it. That's cheating. So what are we going to do? Let's see. We have log of x squared equals 2. One of the fundamental rules about a log is that its argument must be a positive value, right? But here's the good news. X squared is always positive or 0. Of course, we know x can't be 0. That would be a big fat no, because you can't take the log of 0, right? But x squared, as long as you don't plug in 0, is always a positive number. That means we can have positive or negative results because we're going to square them, and then we get a positive. So what we'll do is we'll cancel that log base 10, because it is log base 10, with an exponential base 10 on both sides. Uh-oh, I must have drawn that 0 too fast. The computer thinks it's a skinny 0. Come on, I hit undo. We'll just wait for the computer.
B.
Okay.
Looks like a B or backwards B.
Let's go really slow. There we go. So what we get is that x squared equals 100. Now you just take the square root of both sides. But remember, when you cancel a square with a square root, that creates a plus or a minus. So x equals plus or minus 10. Ta-da! That one is easy. Too easy, right? Way too easy. Yeah, this was lightweight.
Don't say that. You're gonna jinx us, and the next one's gonna be.
Oh, no. My point is, this was so easy, it just didn't scratch the itch. So, oh, there we go. That's better.
Called it.
Mm-hmm. All right. So here we have a logarithmic equation. And what would be your general plan of attack? What do you think? What are you guys thinking? Combine? Yeah, we can condense these.
And
We
then
can condense this because this is the addition of two logarithms with the same base. You know what you're not allowed to do right here? You are not allowed to cancel the ln's the way it sits. You can never cancel a logarithm until it is the only thing on that side of the equation. So right now, having two separate logarithms blocks me from canceling them with the exponential base e. But
could move the 2 ln x over, subtract it. After
well,
you
we
multiply.
could, but hold on. Right now, what we're going to do is we're going to condense our logarithms and write this, instead of the addition of two logarithms, we're going to write it as a single logarithm with a multiplication in the argument. And since we're condensing logarithms on the other side, move that 2 back to the exponent position. Now there's a single logarithm on the left and a single logarithm on the right. This is where you're allowed to cancel. We use base e on both sides to cancel our natural logs. Whee! And we're left with a quadratic equation. So McKinley said we're going to have to bring that thing that's on the right over to the left, and eventually we will, because we can't solve quadratics unless they're equal to 0. On the left side, though, you are going to have to FOIL. Can I just write down what it would equal, since we all know how to FOIL? Okay, great. So it's 3x squared minus 5x plus 2. Just double checking my mental math. Yep. Equals x squared. You see, McKinley, you wouldn't want to have moved that ln of x to the left side because it would have given you a logarithm minus another logarithm, which would have meant you couldn't cancel the logarithms until you wrote it as a single logarithm. And now you've got a fraction. Top of the fraction's got some kind of nasty foiling on the top, and we could still get the same answer, but it's just more work than we want it to be. But here, if we subtract x squared, what we get is 2x squared minus 5x plus 2 equals 0. And oh, yay, it factors. You can use the Lizzie method. I'm going to come over here to the right side because I have more space. Looking for the two numbers that multiply to a times c. A times c is 2 times 2, or 4. And I need those two numbers to add to negative 5. So yeah, there are two numbers that multiply to positive 4 that add to negative 5. Feel free to shout them out.
4 and 1.
Well, 4 and 1 multiplied, there you go.
2, 1.
2 and 1.
They have to both be negative. There you go. They have to both be negative. Negative 1, negative 4. Those do multiply to be positive 4. They do add to be negative 5, so bingo bango. We write our parentheses. And it already says equal 0, so I'll just write the equal 0. X is in the front, fractions in the back. X is in the front, fractions in the back. This is how I've been having the Algebra 2 students do it. They go, since we're doing the Lizzie method, automatically X is in fractions, X is in fractions. The numbers we have go on top. And the bottom of the fraction is the a value, which happens to be 2. I'm actually doing a lot of Lizzie method stuff with Algebra 2 right now. Reducing fractions. Oh goodness, that is not the color I wanted that pen to be. X minus 1/2 and x minus 2 equals 0. It gives us two solutions. X equals positive 1/2 and x equals positive 2. What do you guys think? A hidden quadratic. Again, yay, quadratics. So much fun. Stunned silence is scary. So, what do you guys think? That was lightweight also? Everybody's cool?
It's not stunned, it's just us processing how doomed we are when the test comes.
So everybody's ready to move to the next question? So everybody in the room is happy with half credit then? Yeah, this answer's wrong. Well, partially wrong.
Oh, you gotta check it with.
You have to check your answers because the original question was a logarithmic equation. It has domain restrictions. You have to make sure that your results are allowed to be plugged back in. So let's go back to the top and let's see what our domain restrictions would have been. Okay, well, remember, the argument must be a positive number. So 3x minus 2 must be bigger than 0, and also x minus 1 must be bigger than 0. X must be greater than 1. Oh, that made life pretty simple, didn't it? Let's see, add 2, divide by 3. X must be greater than 2/3. The more restrictive domain is the one that you pay attention to. Of course, this one on the far right is x must be greater than 0. So we have 3 different domain restrictions. The most restrictive is the one that matters.
Wouldn't that be x greater than 2? Would it have to be more than 1?
It could just be 1.1.
Yeah, but you put x equals x is greater than 0.
No, I have the argument must be always greater than 0. So I just set all 3 arguments greater than 0 and then solve for x. Basically, we can't use any answers unless they're greater than the number 1. That answer fails. It's an extraneous solution. This one is the only true solution. So just like rational functions, is it possible to have two correct answers? Yes. One correct answer? Yes. No correct answers? Of course. You have to always check. Neat, huh? Just me. I must be the only person that's impressed by the way log equations work. I love log equations. Okay. Last. Newton's law of cooling. Don't worry. I'm not going to make you memorize the formula for Newton's law of cooling. Can I scroll down? No, nobody's gonna panic? Okay. I'm not gonna make you memorize the formula. If I'm going to have you solve a question using Newton's law of cooling, I'll hand you Newton's law of cooling in the question. Okay? Nobody panic. An object that has been heated will cool to the temperature of the surrounding medium exponentially. So your cup of hot coffee, as long as it's not in an insulated cup of some kind, will cool down to room temperature, and it will get there at an exponential rate. The temperature, capital T, of the object at time, lowercase t, can be modeled by this equation. Woo!
I learned this in geometry.
Yeah, we also do it in algebra too.
I don't
So T sub m is the temperature of the surrounding medium. Usually that means the air. T sub 0 means the original temperature of the object, obviously. And we have lowercase t being time. The only other value that or variable that you have up there is a k. K is basically your cooling rate, because all mediums have different cooling rates. Okay. A hard-boiled egg at temperature 96 degrees Celsius is placed in 16 degrees Celsius water to cool. 4 minutes later, the temperature of the egg is 45 degrees Celsius. Use Newton's law of cooling to determine when the egg will be 20 degrees Celsius. This is actually a very large question. That's why you have the whole bottom of this piece of paper to pull it off. Because you know what I didn't give you? I didn't give you K. So the very first thing you're going to have to do is solve for K. And then once you have solved for K, you could set your equation equal to 20 and solve for time. Yeah, buddy. All right. What do we know? We were told T sub 0. Well, that's green. Well, whatever, we're already here. T sub 0 is 96 degrees. And the surrounding medium, the water, T sub m, is 16. We were given a T, just capital T, a new temperature of the object after a lowercase t. We were told that when time was 4 minutes, just capital T was 45. This allows us to fill out Newton's law of cooling. We have all of the values except for K. This is how we solve for K. So 45 equals 16 plus, parentheses, 96 minus 16, e to the negative k, and then time. So negative 4 time. Oh, k, excuse me. Negative 4k. T was 4. Come on. You can do it. There we go. Alrighty. Let's see. We can subtract 16 from both sides. It gives me 29 equals, and 96 minus 16 is 80, e to the negative 4k. So we're trying to do as much as we can by hand, okay? So we divide both sides by 80. I'm not going to grab a calculator yet because that decimal is probably pretty ugly since 29 is prime. What's next? ln, yeah, we need that e to go away. So if we take the ln of both sides, what we get is negative 4k equals the ln of 29 over 80. So we're going to ln of natural log both sides like so. Of course, over here, those things cancel. So negative 4k equals the ln of this ugly thing. And now you just divide by negative 4. that's where I'd grab my calculator and I would type that in. So I would figure out what the ln of 29 over 80 is and then divide by -4. And the reason why I waited this long is because I want my k to be as accurate as possible. If you round way up here at 29 over 80 and then you take the ln of that rounded number, you're going to be rounding a rounded number. You're basically stacking errors. So I didn't want to touch a calculator to the very end because I wanted an accurate representation of k. And if you take it out to 3 decimals, you are going to be pretty accurate. I got positive 0.253. Something like that. You think you could solve for k reliably? Be all right? Okay. Now that we know what k is, we can use that knowledge to figure out when this object is going to be 20 degrees. So when you come back, you come back up to this line right here, but instead of writing 45 equals, you write 20 equals, okay? So 20 equals, because it was 20, right? Yes, 20. 20 equals the 16 plus 96 minus 16 was 80. E to the negative k, which is 0.253. Unknown time this time. Realize that the answer you get is going to be a rounded answer. So yeah, it's not going to be exact. But the more decimals you use for k, the more accurate your answer will be. And now we just use PEMDAS in reverse order to get t by itself. Subtract 16 from both sides. Ooh, that t got a little janky on me. Divide both sides by 80. Hey, you know 4 over 80 is actually a terminating decimal. So because it terminates, I would just write it as a decimal. 4 over 80 is what, 1 over 20, so 0.05, right? Is it 0.05? Yes, no, maybe so? Not a calculator, people, I need some help. E to the negative 0.253t. So yeah, so that's 0.05 equals e to the negative 0.253. And I think we all see where this is going. Need the e to go away, so we're going to take the natural log of both sides. Whee! Bless you. Negative 0.253t equals the ln of 0.05. And then just divide. So t is the ln of 0.05 over negative 0.253. And like I said, not a calculator, no idea what that number is, so we will look at my notes where I've done this work before. Yeah, I got 11.81.
I did ln 0.5, I got negative 2.995.
But don't round it, just hit divide by negative.
I hit divide by negative 0.253. And I got 11.84.
I got 11.81.
408.
You guys also got 8.4? You know why I got 8.1? Because I never rounded. Instead of using negative 0.253 on my calculator, I actually used this expression for k. I wouldn't expect you to do that because I was really only able to do that because I was using a graphing calculator. But you notice my answer to 1 decimal is the same as your answer to 1 decimal when you round, isn't it? The reason why? Because I use 3 values, 3 variables. Help me, please. 3 decimals for k. See, generally, if you use 3 or more decimals, your answers are pretty darn accurate. So let's just call it about 11.8. On the test, if I was going to ask you to do this question, I would be very specific about when to round and how many decimals to round to. So about 11.8 minutes. And that's it. That's it for the notes. Solving log equations, solving exponential equations, not that bad.
There's another section.
There is
Actually,
one more, two more sections actually. We have to do 3.6 and 3.2 still. But tomorrow we will be practicing everything we've done so far in this chapter. So 3.1, 3.3, 3.4, 3.5, practice tomorrow.